Yeah. But there was something example like that, and that. I mean, some of the main ball like yeah, yeah, like that. And you talk about like skeleton. Oh yeah. I that. Oh, I'm so learning that. I'm going like a skeleton. Um,
All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, good, hanging in there. All right, so we are a week out from our midterm exam. We have one more part of the body to go over, which is the spine. So I'm thinking that probably today we're going to spend talking. We'll get halfway through the spinal stuff, and then we'll finish the rest of it on Monday. So the timing is going to be a little bit tight. But in terms of the exam itself, the majority of the exam is going to be static analysis, and so we've kind of had plenty of practice with that at this point. If anything, most of the relevant stuff that's going to be on the exam is we're going to go over today. So just the general characteristics of the spine, the general structure of the bones. That's the stuff that's kind of really new. And then we're going to move on just to doing more practice problems with static analysis. Okay. All right, so that's the plan for today. So some announcements. I posted the solutions for homework 1 and homework 2. So those are on Canvas for you. So if you go onto the Canvas page for week 6, you'll see the homework 1, homework 2 solutions there. I'm going to post the solutions to homework 3 on Monday after the homework is due. Okay. All right. Any questions I can answer before we get started? Okay. All right, so let's go ahead and get started. So actually, let me go ahead and switch to the PowerPoint here. Okay, slideshow. Okay. All right, so this week so today and Monday, we're going to be talking about the spine, right? So we've finished talking about the upper extremity, the lower extremity. The spine, some may consider to be part of the upper extremity, but really it's your core, right? So even though we're focusing on the spine, this is really kind of everything that has to do with the core of your body. Okay. Okay. So the spine itself has a lot of really important functions that it serves for the body. And so besides the lower extremity, the spine is the other kind of major load-bearing structure in your body. And so basically the entire weight of your upper body is kind of placed on the spine itself. And if you think about it, there's if you kind of separate kind of the torso and the lower extremity, the only bone that really connects them is this spine. So oops. So all the way from the chest and the head and your arms, all of that gets concentrated on the spine right here. So, your spine is responsible for bearing all that load, and so it has to have kind of a lot of strength. Okay. And so that kind of leads into point number 2, where it's basically the major kind of mechanical linkage between the upper and lower body. Okay. And the third function, and this is the one that people normally associate with the spine, is that it protects the very delicate and very vital spinal cord, right? So your spinal cord is basically this very kind of large bundle of nerves that kind of goes from your brain and it goes through the rest of your body. So it's kind of a thick, you can almost think like a thick wire that kind of runs through your spine right there, right? And it's kind of central to your nervous system, where if your spinal cord gets damaged, then your brain is going to have a hard time communicating to the different parts of your body, controlling your muscles, controlling your organs, and things like that. So your spinal cord is a really important part, and it's really important that it's very well protected. And that's what the spine and the vertebrae basically does. Okay. Okay. So there's a specific portion of the spine that we're going to focus a lot on, which is the lower part of the spine. So we call that the lumbar spine, right? So you probably heard that term before when you talk about ergonomics, excuse me. And so people always say you need lumbar support when you sit. You need lumbar support, otherwise your back's going to be hurting. The lumbar spine is definitely the most interesting biomechanical part of the spine itself. And a lot of devices, a lot of attention, a lot of treatments are kind of focused on that lumbar spine. Okay. There's a lot of very large muscles that are governed by your core as well. And so you have your abdominal muscles, your back muscles, your lateral muscles. Okay. So we'll talk a bit about those as well. And the spine itself is divided into 5 different sections. So we'll go into this a bit more detail later, but each of the sections of the spine are governed by basically whenever the spine changes curvature. And so you can see on this upper portion here, the spine kind of curves, towards the back, and then in your chest area kind of curves towards the front, and then towards the back, and then towards the front again, right? So each time that the spine changes curvature, that's kind of a different section of the spine. And each section of the spine has a different, different characteristics that we'll talk about. Okay. Okay. So let's talk about the bones in the spine. So, this part is actually quite simple. So all the bones in the spine have basically all the same shape, and they're all just kind of stacked on top of each other. And so these are your vertebrate bones. So when people talk about the vertebrae, they're usually when people refer to the vertebrae, they're talking about the entire, stack of all the vertebrate bones. But, specifically, one vertebrate corresponds to kind of one of these bones here. Okay. So on average, people have around 33 vertebrates stacked on top of each other. And they're labeled based on what section that they're in and which bone that they are, right? So this top section right here, this is the one that connects up to your skull and your head. This is known as the cervical vertebrae. And so the cervical vertebrae, there's about 7 of them. And so they're labeled C1 through C7, right? So the top one is C1, second one is C2, C3, C4, C5, C6, C7, okay? So the naming convention for the spine is actually, quite simple, right? The next section of the spine is the largest section. So that is your thoracic vertebrae. So this is the section of the spine that's basically right behind your chest. So you have 12 of these, and they're labeled T1 through T12, okay? At the bottom of the spine, you have your lumbar spine. So this is the kind of the most important section. This is where a lot of the load, a lot of the forces are being applied on the spine in general, okay? So that's L1 through L5. A lot of the injuries that people sustain are usually, usually around, L1, L2, L3. Okay. And then the last 2 sections of the vertebrae are actually, technically they're different bones, but by the time you reach adulthood, these bones kind of all fuse together into one. So they can't really move past each other like the other bones can. So you have 5 sacral vertebrae. So that is basically the vertebrae that are kind of in this section right down here. Okay. So that's S1 through S5. So S1 through S5, these are they're originally separate bones, but as you kind of grow and mature, then they kind of all fuse together. Very similar to how your skull works, if you remember that. Okay. And then at the very end, you have your tailbone, which is the coccyx bone right at the bottom there. Okay. And it's the same kind of thing. So even though there are technically four separate bones there, they all kind of fuse together into one. Okay. So there's not really a lot of movement down here. But the reason you can kind of bend your back forwards and backwards is because there's some movement that's allowed between the vertebrate bones in the cervical, thoracic, and the lumbar spine. Okay. So these are kind of the average numbers. So most people have these numbers of spines, but there is some kind of person to person variation as well. Someone may have one extra lumbar spine or one less lumbar vertebrae. But on average, these are kind of the numbers that we expect. Okay. Questions?
So does that normally mean you have one less somewhere, or just an extra bone?
You just have an extra bone.
Okay.
Yeah. Yeah, so you have an extra lumbar. It's not like it's compensated anywhere else. It's just you just have an extra one there. Yeah, that's usually for the people who are taller. So taller people have a longer spine. So there's kind of an extra one there. Okay, so let's talk about the structure of the vertebrate bones themselves, because they actually have quite an interesting structure, right? So like I mentioned, all the vertebrate bones, they all have the same structure. They vary in size, of course. So your lumbar vertebrae are going to be bigger than your cervical or your thoracic vertebrae, and that's mostly just because they have to support a much bigger load. Okay. Okay, so if we look at kind of the structure, so the structure of the vertebrae, if you look at it from the top, is given by this image in the bottom right here. So every vertebrate bone has a body, and so the body takes up most of the volume and most of the mass, right? So it's pretty big because the vertebrae is a load-bearing structure, right? So it needs kind of a good amount of girth in order to do that. Okay? There's a hollow ring. So there's a ring that is basically hollow. So this is where the spinal cord passes through, right? You can see kind of a side view here a little bit better. And so, the hollow ring for these vertebrate bones are basically right here, okay? And then you can kind of see the spinal cord kind of pass right through the middle of that ring, okay? So you can see that the vertebrate bones kind of surround the spinal cord on all sides. So it's typically very well protected, okay? And then besides those two structures, there are additional kind of, I call them kind of appendages that kind of stick out from the outside, and they kind of play kind of an important role as well, right? Okay, so in general, most, basically all your vertebrae have this same structure right here. The only exception is that the first two cervical vertebrae, so that's C1, C2, up near the top of your spine, they have a little bit of a specialized shape so that, your skull can kind of fit on top of the vertebrae. Because your skull kind of fits, it attaches directly to your spine through C1 and C2. Okay. Okay. Another point, like I mentioned that generally as you go from the top of your spine to the bottom, the vertebrae are getting larger in size, so they get larger in diameter and larger in mass, right? The reason for that is because everything below has to support all the weight of everything above it. Okay. So your lumbar spine are going to be much bigger than your cervical spine. Okay. And these bony appendages, they support some load bearing, but their main purpose is to basically limit the range of motion for your spine, right? So as you can imagine, your spine is a very important structure, right? And so it bears a lot of force and it protects the spinal cord. So kind of a self-defense mechanism that your spine has to kind of prevent yourself from twisting and turning too much is the fact that these kind of bony appendages kind of they kind of bump each other once you kind of bend back too much. Okay. So if you notice, it's always much easier for someone to bend forwards than to bend backwards, right? So if you try to bend backwards, there's only so far you can go, before you start feeling pain and stuff. So that sensation of pain and that the fact that you can't bend as far back as much is the fact that your vertebrate bones, once you bend backwards, you can imagine that when you bend backwards, this vertebrate bones kind of rotate kind of this way, right? And so this part of the vertebrate bone will start to kind of contact this one. And once they're in contact, it kind of prevents any further motion, right? And so the idea with that is that, if you, that motion is there, or that kind of action is there, because, if you bend back too much, you kind of put yourself at risk of kind of damaging your spine or damaging your spinal cord, okay? Yeah, question.
So how can some people do like back bend and others can't if it's only your vertebrae section?
Yeah.
There's also a muscle between there.
There's some muscle too. So some people have stronger back muscles that allow them to kind of push past that as well. Some people just have kind of smaller appendages too. So there's kind of variation between different people in terms of how big these bones are. So yeah, this is kind of the general shape, but there's always going to be person to person variation as well. Mm-hmm. Yeah, whenever I see people kind of do like contort it always I have a very weak stomach, so I can never watch someone do that and kind of feel okay with myself afterwards. All right. Any questions on this? Okay. Oops. Okay. So another important part of your spine are what are called these intervertebral discs. So in between each of your vertebrae, you don't have bone-on-bone contact between your vertebrae. In general, I mean, your appendages may contact each other during certain motions, but the majority of the weight is borne by the body of the vertebrae. Okay, and as you can imagine, as you kind of go throughout your day, there's a lot of force that gets impacted on your spine. And so if you have bone-on-bone contact, for a large portion of the day, supporting a very large amount of weight, that's going to lead to a breakdown of the bone very, very quickly. So just like, most of the other joints in your body, there's some kind of protective, tissue or some protective cartilage in between the vertebrate bones. Okay. So in between the vertebrae, we have this kind of very fibrous tissue called a disc. And so, the cross section of the disc kind of looks like this. And so it has kind of a very, almost kind of like an onion type of structure here. Okay. But the whole idea of these discs is that, they provide kind of like a cushion in between your vertebrae. Okay. And so, some people think of them like a spring. And so their whole idea is that, when your spine gets compressed, that instead of, your vertebrae bones kind of contacting each other, instead, these discs kind of act like a kind of a soft cushion that kind of, kind of squeeze out and kind of cushion that load. Okay. So your discs are a very important part of your spine. If you think about, how often that you kind of get up and sit down, even when you're walking, right? So even when you're walking, you kind of place some kind of compressive force on your spine, okay? Even more so if you're going to be doing any kind of physical activity. And so these discs are a very important part of making sure that your spine kind of functions properly, okay? Okay, so these discs are often injured, right? And so we'll talk about injury to the disc a bit later, but you've probably heard of the injury called a hernia. So basically, when someone has a hernia, what happens is that the kind of the fibrous structure of these discs kind of start to break down after repeated kind of impacts, and then it starts to kind of bulge outwards. And so, sometimes your disc can be squeezed to an extent that, some of it starts to kind of leak. It kind of looks like it's kind of leaking out like that, right? In the worst case, you could have a disc just completely slip out. And so, you probably heard of people getting a slip discs. That's pretty extreme. That's usually very, very painful. But even a hernia can be extremely painful as well. Because what tends to happen is that, once this disc starts to bulge out, remember, what's inside this cavity right here is your spinal cord, which is basically a gigantic bundle of nerves in your body. And if you know anything about nerves in your body, they really don't like to be touched in a way that they're not comfortable with. So if the spinal cord feels the disc or anything kind of impinging on it, it's going to send a really big danger signal to your brain, that, hey, something's not right. I'm not supposed to be, this is not supposed to be happening. And so that kind of triggers a huge kind of surge of pain. And so if you've, probably no one here has had a hernia yet, but if you know someone that's had a hernia, it's extremely painful. And it kind of, makes it so that you can't really do anything throughout your day. You're kind of just immobilizing in your bed. So yeah, definitely something to look out for. Let's see. Yeah, and so in some of the examples that we're going to do later today, we're going to talk about things like having proper technique when you lift a load off the ground, right? I think nowadays, people are pretty aware of it, that when you're lifting, let's say a heavy box off the ground, you should lift with your legs, don't lift with your back, right? So we're going to do a couple of examples that kind of show, how bad that actually is. Okay, because generally speaking, these discs, if you apply enough force to them. And so if the joint reaction forces at these discs are high enough, that's usually what's enough to cause a hernia or some kind of injury. Okay. And so whenever you're doing any kind of physical activity, you always want to do it in a way that kind of, does not place a lot of stress on your back. And so we'll talk about kind of techniques for doing that in the examples. All right. Any questions on this? Okay. Okay, so curvature of the spine. So this is another kind of important characteristic of the spine to know, right? So your spine has this very natural curvature that it's kind of optimized for kind of doing everything that your spine needs to do. So this is optimized for load bearing, optimized for protecting the spinal cord, and this is kind of just based on the structure of the vertebrae bone. So a normal kind of spinal alignment kind of looks like this. So you have a little bit of curvature in each of the different sections, but it's never too extreme. Okay. Of course, the curvature of your spine is not a static thing. And so you can definitely alter the curvature of your spine, based on kind of the actions of your muscles, right? And the different positions of the spine, scientists have given different names to them. And so the first one is lordosis, and so you can kind of, this is kind of the position that people generally recommend when you're trying to, straighten up your back. And so when you're straightening up your back, generally people, what they do is they kind of emphasize the lumbar curvature of your spine. And so you kind of stick your chest out, and then you can kind of feel your lumbar spine kind of that curvature kind of get exaggerated. Okay. So that position of the spine with an exaggerated lumbar curvature is called lordosis. Okay. So lordosis by itself isn't bad. Anyone can do it, right? And so as long as you kind of stick your chest out, that's kind of the motion. What is called pathological lordosis is, when someone isn't trying and they kind of just try to just stand up straight on their own. If their spine kind of has a natural lordosis curvature, that's what's called pathological lordosis. Okay. And so for those people, that's usually attributed to having either weak abdominal muscles, or some kind of tilt in their pelvic bones that's kind of not normal. Okay. And so if you have pathological lordosis, you may consider something like physical therapy to kind of help with your posture, to kind of straighten your spine into something that's a bit more healthy, a bit more sustainable. Okay. All right. So another term for spinal curvature is kyphosis, and so kyphosis is an exaggeration of the thoracic curvature. Okay. So this is kind of, I think kind of what people associate with kind of having someone being humpback, right? And so if you kind of slouch your shoulders a lot and you kind of, don't stand up straight, this is kind of what it kind of looks like. Okay. So there's kind of, normal kyphosis where someone just naturally kind of droops their shoulders. But of course, there's also pathological kyphosis as well, when their spine is just kind of naturally like that. And so again, that's something you may want to do physical therapy for, or do some kind of treatment to kind of, put your spine into a more healthy alignment. Okay. And so this can be caused by something like a congenital abnormality. So congenital abnormality means, maybe your spine was kind of born in a certain way that kind of has that abnormal curvature. Or maybe you're kind of later on in your life and you have osteoporosis. Okay. So it's fairly common that you see kind of older people kind of hunch their back a little bit. So they kind of have this kind of exaggerated thoracic curvature. And it's because their bones are not strong enough to kind of maintain a healthy posture from there. Okay. Okay. So lordosis and kyphosis, these are relatively normal. These are kind of relatively fixable. But probably the condition that you've if you've gone to school in America, you probably know this is scoliosis. So scoliosis is a very abnormal curvature where your spine actually curves to the side. So your spine's not supposed to do that. It's only supposed to curve kind of front to back. And so if you were, I think they still test for this in schools. Probably there was at some point when you were growing up where you had someone come in, like the school nurse, and they kind of check your spine for any kind of scoliosis. Okay. And so this one you definitely want to catch early. You definitely want to catch it in your developmental years, because if you kind of grow and you kind of mature into an adult, and you have scoliosis, it can cause a lot of problems in just your quality of life. And there's not much you can do kind of once you're fully grown. So it's often tested for a lot in children. I think it's even part of the standard panel for little kids when they get their checkup, because this is something you want to check early and you want to get it addressed. Okay. All right. Any questions on this? Okay. Okay. And so very quickly, let's go over the muscles of the spine or the core. Okay. So a lot of the muscles in your spine and your core are not really muscles that you think about kind of exerting on a regular basis. Maybe when you're working out. So people like to work out their abs, they like to work out their back. So that's when you kind of think about it. But actually, these muscles are almost always engaged to a certain degree, because these are the muscles that are mostly used to maintain your posture. maintain your posture, and maintain your balance, okay? So even when you're not thinking about it, your spinal erector muscles, which are these kind of muscles kind of in the back here, we're gonna be talking a lot about those. Those are often acting to kind of make sure that you're standing, you're kind of upright and you're not kind of falling over, okay? But we also consider the abdominal muscles as part of the core, and your oblique muscles too. So your oblique muscles, they're not really shown here. Your obliques are kind of on the sides of your of the body, right here. Okay. Okay. And so in particular, we're going to place a lot of emphasis on these spinal erectors because, if you look at the part of the spine that they connect to, right underneath these spinal erector muscles are your lumbar spine. Okay. Okay. And in fact, if you kind of look at the attachment of these spinal erector muscles, they kind of their inferior attachment is kind of right on your pelvis bone, and then their superior attachment is kind of near the top, kind of the upper area of the lumbar spine and kind of the lower area of your rib cage. Okay, and so what tends to happen is that when these spinal erector muscles contract, right, and so when they're exerting force, they're basically squeezing all of your lumbar spines together. And so if your spinal erector muscles are, working a bit too hard, and so if they have to exert a lot of force just to maintain, static equilibrium in other parts of your body, that's going to put a lot of stress on your lumbar spine. And so, generally the recommendation for people is that, if you're going to be doing, work that involves kind of moving things around, or let's say that you're just kind of lifting a lot of heavy things, you want to do it very carefully. Otherwise, you're going to hurt yourself. Okay. So one example of this is that if you go to the gym a lot, you probably either you've done them yourself or you've seen people do deadlifts. You have to be really careful when you do deadlifts, and you want to make sure your posture is right, because if your posture is not good, if your technique's not good when you do deadlifts, what's going to happen is that you're going to kind of engage your spinal erector muscles, kind of in an imbalanced way, and especially if you're not engaging the other parts of your core. And then, when your spinal erector muscles are working too hard, that places too much stress on your lumbar spine, and that's usually what causes people to get hurt doing deadlifts. Okay? So deadlifts, probably if you worked out, probably people have kind of drilled this in you. You want to be careful doing those. And so, we'll go a bit more into detail about why that is. Okay. All right. Any questions on the muscles of the spine? Okay. Let me go ahead and clear this. Oops. Okay. So let me go ahead and switch to the iPad. I wasn't sure if I had one more slide after that. And let's go ahead and start doing some examples. Oops. I stopped recording. Okay. So let's do some examples to kind of show you kind of kind of the dangers of doing certain actions on your spine. Okay. So, we've already seen from the lower extremity, mostly in the lower extremity, that your muscles are capable of exerting, very large magnitudes of force. Okay. Okay. And a lot of times that's needed because, if you remember, the moment arm for a lot of these muscles are very small, right? So they attach very close to the joints in which they act upon, right? And so if you have any kind of external force that has a much larger moment arm, in order to kind of balance that out, your muscles have to exert a very large force. Okay? And so in some ways, that's good because, if and we kind of talked about it with the analogy with the drawbridge, if you need to kind of move your limbs very quickly, you're able to do that because of the way your muscles and are the way your muscles attach to your joints. Okay. But that kind of has a secondary effect where, a lot of muscles, they don't, the way that they're attached to the bones, there's usually a significant portion of the muscle force that kind of pushes your joints closer together. Okay. So we've seen a lot of examples of this as well, right? And so usually, when you have a joint, so let me kind of draw an example here. Okay. Right. So let's say that we're looking at, this could be the knee, this could be the elbow, it doesn't really matter. Okay. A lot of times, you're going to have a muscle force that kind of acts something like this, right? Where this is the attachment angle, theta M, and the moment arm here is L M. Okay. All right, if I were to break this muscle force up into its different components, right? And so what we've done usually is we usually break up this muscle force into a component that's perpendicular to the body segment. Okay. Okay, so I'll call that F perpendicular. Okay. Usually this is the one that we're interested in because this is the component of the force that's going to generate a moment, right? So this is the one we usually use in our static calculations. Okay. One component of this force that we haven't really talked too much about is the parallel component. Okay. So I'll call that F parallel, right? And so if you look at this force right here, the way that it's pointing, it kind of pushes the body segment back into the joint. Okay. Now we know from Newton's laws that whenever you have a force, there's always going to be an equal and opposite reaction force as well. Okay. And so we've computed those as well. Okay. And so in order for this entire, system here to be balanced statically, there has to be some reaction forces at the joint, Jx and Jy. Okay. Okay. We haven't really talked about these all that much, and in fact, just because of time constraints, I think for a lot of the past examples we've kind of skipped them. Okay. But these are going to be really relevant here. Okay. Because what the joint reaction forces kind of show is that that's how much force, basically that's how much compressive force that your joints are being subjected to. Okay. And whenever you have a large reaction force like that, that has to be absorbed by some structure within the joint itself. Okay. Okay. So that phenomenon, hasn't really been relevant to anything that we've talked about so far, because for the most part, all the joints in the lower extremity and the upper extremity, there's not that much danger for compressive injury in those cases. Okay, but there is such a danger in the spine. Okay? And the reason for that is because of all the intervertebral discs that exist between the vertebrate bones. All right, so it's not that the discs are any weaker than any kind of other tissue in your body. It's just that your spine is subjected to so many forces throughout the day. Even just kind of just sitting up in your chair, your spine is under some force, right? And so, when I'm talking about kind of the forces that your spinal erector muscles are placing on your spine, that's kind of extra forces that your spine has to sustain in addition to just bearing your weight. Okay. So you want to be careful about that, and you want to be careful how much force that you're applying to those bones. Okay. Okay. So let's do an example, right? So with that in mind, let's take a look at some numbers here. Okay. So in this example, we're going to examine proper lifting technique. And I don't mean weightlifting in here, although you can do weightlifting like this. What I mean is, lifting a relatively large weight from the ground up into your arms. Okay. So the general, kind of the general advice that people give to you, you take any kind of safety training, they'll tell you, is to lift with your legs, right? Not with your back. Okay. And so let's say that you have a load, then you say picked up off the ground. Okay. So generally the poor way to do this, or the poor technique, is to basically bend over at your back and try to lift it up that way, right? This is the bad way to do it. And kind of, qualitatively, you can kind of see why, because, if you were to lift this up, right? So let's say you pick it up and you kind of, lift it up by rotating your body this way, right? The only muscle that's doing that is your spinal erector muscles. Okay. That's the only muscle there that's basically allowing your torso to kind of rotate backwards, right? And that is one muscle that you don't want to put excess stress onto, because once the spinal erectors are compressing, that's going to compress your lumbar spine as well. Okay. So that's why this technique is not good. Okay. And so the general kind of technique that people recommend, so let's say that we have our load here again, okay, is to kind of try to get as close as you can to the load that you're picking up. Okay. Bend downwards at your legs. Try to maintain kind of a straight back. Okay. And then kind of lift it up that way while maintaining your back posture is straight. Okay. Okay. So what we're going to do is we're going to put some numbers on this, and kind of just to illustrate, how bad this technique is and how much it kind of saves your back by doing the good technique. Okay. Okay. So let's look at bad technique first. Okay. So I'm just going to focus on just the, we're focusing on the spinal erector muscles, but, just to make a complete picture, we have to draw the entire lower extremity. Okay. So if you're lifting with bad technique, usually your legs are relatively straight and you're bending down only at your back. Okay. So it looks a little something like this. My drawing in the actual notes is actually not bad, but whenever I go to draw in the lecture, it always ends up looking really awkward. So let's see if I can. Oh, that's not bad. Definitely could be worse. Okay. Well, that last part was kind of weird. Whatever, close enough. Okay, so what we're doing is you're looking at someone on the side, okay? We have our spinal erector muscles kind of acting at the end here. Okay. So that's FM. The joint that we want to examine is your lumbar spinal joint. Okay, so that's kind of up here. So relative to your hip joint, it's going to be further up. Okay. Actually, let me make this a bit better. There we go. Okay. All right, so your hip joint would be kind of somewhere down here, right? So we're not considering the hip joint, we're considering the spine, which is above. Okay. So at the spine, we're going to have our joint reaction forces up there. Okay. So we have JX and JY. Okay. Just for the sake of simplicity, I'm going to give you the moment arm for the muscle force. Okay. So this distance, this perpendicular distance between the force vector and the hip joint, or excuse me, the spine, we'll say is a distance A. Okay. And then in addition to that, we're going to say that the direction of the muscle force is going to be given by theta m with respect to the vertical. Okay. Okay. And so in addition to that, we have our external loads. Okay. So because of the way we drew this figure right here, we're not including the external load directly. But the way that we're going to account for it is that, in order for the load to, for your body to support the load, there has to be an equal and opposite reaction force from the ground. Okay. So what we're going to assume is that there is a force that's being applied right at the tip of your toes. Okay. So this is going to be the weight of your torso plus the weight of the load itself. Okay, so we'll call that WL. And then we also have the weight of the lower extremity as well that we need to consider. Okay. So we're going to assume that the weight of the lower extremity acts right here. Okay, so we'll call that weight load. Okay. We also need to know the distances here. And so if we draw kind of a dotted line that comes down from the spinal joint. Okay. This distance in between the vertical line for the spine and the weight of the leg, we'll call that B. Okay. And then this distance in between the spine and the external loads, we'll call that C. Okay. Just because there's a lot going on here, let me go ahead and draw this over here, okay, just to make it a little bit easier to see. Okay. So here we have our spinal joint. So we have JY and JX. Okay. And then we have our muscle force. Okay. Muscle force is acting just like that. Okay. We know the distance, the perpendicular distance between the muscle force and the joint. Okay. So we call that A. And then the direction of the muscle force will be theta m. Okay. That's just, that's just a blown up version of kind of what's up top there, just because the image there is a bit busy. Okay. Okay. So let me do this too. Let me not forget to give you all the dimensions. Okay. So all the given information, we are given all the physical dimensions and measurements here. Okay. So A, that distance will be 0.02 h. Okay. H is the height of the person. Okay, so everything here is going to be measured relative to the height of the person itself. Okay. B here is going to be 0.08 h. And C is going to be 0.12 h. Let me close that. Okay. Let's see what else do we have here. So we have the weight of the leg, or the weight of the lower extremity. So this is going to be 0.4 W. Okay. So everything here is going to be measured relative to the weight of the torso. Okay. So W there is the weight of the torso. Okay. So weight torso is equal to W. Okay. And let's say that the weight of the load here is 0.3 W. Okay. So we're attempting to pick something up that's about 30% of the weight of our torso. All right, and the last thing that we need here is theta m. So we'll just assume theta m is 45 degrees, just for simplicity. Okay. Okay. So given all this information, let's go ahead and start solving this problem. So what we want to do is we want to compute. Okay. We want to compute our muscle force, Fm, and our joint reaction forces, Jx and Jy. Okay. It's a very typical problem, it's just kind of within a different context here. Okay. All right, any questions on the setup of the problem? Okay. All right, so let's go ahead and solve this. All right, so just like we usually do, let's start with the moment equation. So let's write out the moment equation just so we can solve for the muscle force. Okay. All right, so we sum the moments around the spine. Okay. So the way that our moment arms in this problem are given to us is very convenient because we don't have to do any kind of components in terms of x and y, right? All the distances here are given perpendicular to the vectors. Okay. So I'm simply just going to take the product of each force multiplied by its moment arm, and give its appropriate size as well. Signs. I mean. Okay, so let's start with Fm. Okay. So we know Fm here is going to rotate clockwise around the joint. Okay. So it's going to be a minus Fm times A. Okay. Next, we have the weight of the leg, or the lower extremity. Okay. And so if we kind of trace this around the joint, we can see that it's going clockwise. And so we have a minus W low multiplied by B. Okay. And then by process of elimination, just because you can't have all negative moments, and it's a static situation. We know that the combination of weight torso plus WL has to be positive, and we're going to multiply that by its moment arm, which is C. Okay. All right, but of course, you can verify that direction too. So if you go back up to the figure, we can see that W torso and WL, they rotate counterclockwise around the joint. So it should be a positive moment. Okay. Okay. So we have this algebraic equation. The only unknown here is Fm. So let's go ahead and solve for it. Okay. So I'm going to move Fm to the other side of the equation. Okay. So if we add FMA to the other side, I'm just going to go ahead and divide by A as well. So this is going to give us W torso plus WL multiplied by C minus W low times B, all divided by A. Okay. Okay. We have the numbers to plug in here, or at least everything that's kind of relative to the torso weight. Okay. So if we plug in all of our given quantities here, okay, so if we plug in everything, what we get is FM is equal to 6.2 W. Okay. So what is this result telling us? And so what this is telling us is, when you're lifting a load from the ground, and you're using relatively bad technique, then your muscle force, your spinal erectors have to exert a force that's 6.2 times the weight of your torso. Okay. So just to give you some perspective, for a typical person, so a typical person, about 2/3 of their weight is kind of centered on their torso. Okay. So for someone with a total weight of around 160 pounds, their torso weight is usually around, 100 to 110 pounds. Okay, so let's say 110. Okay. All right. And so if our torso is 110 pounds, right? Remember what we assumed in this problem was that the exterior load has a weight that's about 0.3 times your torso weight. Okay. So WL is going to be around maybe 30, 35 pounds. So if you think about, lifting something that's 30, 35 pounds it's not trivial, but it's also not the heaviest thing in the world too. So, the way I like to think about it is, one thing I have to buy a lot because I have 2 cats is I buy, big boxes of cat litter all the time. And those cat litter boxes weigh 35 to 40 pounds. Okay. So pretty typical, right? And so generally most able-bodied people are expected to carry something like that from Target into their car, and then from their car into the house with no help from the wife at all, because she says, I'm the guy, right? So if I were to lift that box of cat litter with just, with poor technique, right? That means my spinal erector muscles, they're exerting somewhere in the ballpark of, 650-ish pounds, okay? Okay. So that's a lot, right? And so for one muscle to exert, we're not strangers to having our muscles exert large amounts of forces. So, that part isn't surprising. But this is kind of one big muscle and kind of one very sensitive area in your body. Okay. So let's see what kind of consequence that has on the joint itself. Okay. Okay. So let's sum up the joint reaction forces. And we haven't done this together in a while. So this is kind of nice. Okay. Okay, so let's sum the forces in the x direction. Okay. So luckily for this problem, there's not that many forces in the x direction here. All we have is Jx. Okay. And we also have the x component of the force itself. Okay. Now you have to be careful a little bit here, because if you look at the angle that's given to us by the forcing vector, that angle theta m is given with respect to the vertical, right? It's not with respect to the horizontal. And so in order to get the horizontal component of Fm, we're going to take Fm sine of theta m. Okay. And set that equal to 0. Okay. And so we have a relatively simple equation. So we have basically Jx is equal to minus Fm sine theta m. Okay. So we have our answer for FM above here. So I'm going to just do everything in terms of W still. Okay. And so what we get is Jx is equal to negative 4.38 W. All right. So notice our result here is negative. So all that really means is that our chosen direction for Jx is incorrect. Okay. So if you go back up to the figure, right, we've kind of automatically assumed that our Jx pointing to the right, right, and that sign there was active in our force equation. Okay. So the fact that our result here is negative, all that really means is that Jx actually points in the opposite direction, right? So it has the same magnitude, so it has the same magnitude of 4.38 W. Okay. It's just that the correct direction is going to the left as opposed to the right. Okay. So don't be alarmed, if you get a negative answer for a joint reaction force, all it means is that it's just the opposite direction. All right, and let's do the same thing in the y directions. We're going to take some of the forces in the y direction. Okay. Okay, and so if we do that, we have a few more forces here. So we have Jy plus Fm cosine theta m. We have the weight of the lower extremity, W low. And then we have the weight of the torso going upwards. Okay. Remember, we applied that force as a normal force coming from the bottom, and the weight of the load itself. Okay. Okay. So once again, this is a fairly simple equation. We can just solve it for Jy. Okay. So if we move everything to the other side of the equation, we have minus Fm cosine theta m plus W low minus W torso minus WL. Okay. We plug in all the numbers for that, we get minus 5.28 W. All right, so once again, we get a negative result. The negative result just means that, our direction for Jy is the opposite. Okay. Okay. So we can take these two things and we can compute the magnitude of the joint reaction force, right? And so that's oftentimes really useful because you often want to know kind of what the total force is. Okay. Okay. And so to take the magnitude, we're going to take square root of Jx squared plus Jy squared. Okay. Just taking the magnitude of those vector components. Okay. And what we get from this is 6.86 W. Right, so you can see that's a massive amount of force that's being placed on your vertebrate bones. Okay. Not only is it very large, but we haven't really considered this all too much. But in this position here, with your back kind of bent over like that, your spine is actually in a very kind of vulnerable position. Okay. So when your back is kind of bent over, or I should say hunched over. Okay. Remember, your spine is nothing more than just a stack of all these different vertebrate bones. And when you kind of hunch over, then those vertebrate bones kind of change their alignment as well. Okay. So, the way I think about it is that, they have to kind of arrange themselves in an unbalanced formation, okay? So what do I mean by that? So normally, when you're standing up straight, your vertebrate bones are all stacked on each other nicely like this, okay? Right? So this is normal posture. Of course, I'm using rectangles here to approximate the spine, okay? When you're hunched over, right, all these bones have to rotate themselves a little bit. Okay? Okay. And so it ends up being something like this. Okay. So why is this bad, right? First of all, we know that in this configuration, we have just a massive amount of force that's compressing these bones together, okay? So that right there is our joint reaction forces. Okay. So that's already a bad thing. But if you look at how this is arranged, right? If you look and see how this force is being applied, these vertebrate bones are not really stacked straight on top of each other, right? They're all lopsided. And so when you apply this compressive force, it's going to do so unevenly across your vertebrate bones, okay? And so for the parts that are scrunched up together, like right here, okay? Let me use a different color here. Okay. So for the parts that are scrunched together, when you apply this large compressive force, that section of the vertebrae is gonna experience a much larger force compared to the other side. Okay. Okay. And so the back side of your spine is actually okay, and so it's relieved of its tension a bit. Okay. But remember what exists in between here, right? So in between your vertebrate bones is the disc, right? Right? So you're going to have these little disc cushion pads in between each of your spines here, right? And if you're applying this force, I mean, first of all, you're applying a very large amount of force. But if you do so in this unbalanced way, then, you have one side of your cushion experiencing much larger forces than the other, okay? Now, this by itself is not such a bad thing. And so you are capable of doing this. So, don't be scared of picking something up, from your back. Your spine is more robust than that. Okay. The issue comes when you put your body through this over and over and over again. So if you lift with poor technique and you do it many, many times, what tends to happen is that, because this section of the disc here experiences a disproportionately large amount of force, then that side of the disc tends to fatigue a lot more easily. Okay. Then this is when, when this part gets fatigued, a lot of the fibrous structure in the disc starts to break down. This is when this disc starts to leak out in this direction. Okay. All right, so lifting with poor technique is a double whammy. So on the one hand, just because you're lifting with technique, your spine is just experiencing just a very large amount of force, but also just in the posture that you have, that force is not evenly distributed across your vertebrate bones as well. And so, this is what causes a lot of issues with the spine. Okay. All right, any questions on this example here? Okay. All right. So for the last example that we're going to do today, let's see the same situation, but with better lifting technique. Okay. So remember, the proper lifting technique is that instead of bending over your back, bend your legs as much as possible to try to keep your back as straight as possible. Okay. And what you're going to see is that actually the key part of this is actually keeping your back straight. That's the part that's going to alleviate a lot of the stress. Okay. Okay. So once again, let me go ahead and draw this person here. Okay. So a person kind of crouching down may look something like this. Okay. Okay. Not bad. Okay. So once again, we're going to draw the spinal joint. So the spinal joint is going to be somewhere up here. Okay. We have our joint reaction forces, JY, JX. Okay. Now, we can use the knowledge from the last problem to know that, the joint reaction forces are probably going in the opposite direction. But, we'll just kind of keep it like this just for the sake of consistency. Okay. We have our muscle force. Okay. So our spinal erector force is kind of directed kind of parallel to the back. Okay. So that's FM. Once again, the FM here is going to be angled with respect to the vertical. We'll call that theta M. And we have this distance right here. Okay. Now, because your back is straight, what that basically does is that it puts your spinal erector muscle in a much better alignment, right? And so your muscle here is actually able to act kind of, with a slightly larger momentum than before. Okay. So I'm going to call this A2. Okay. A2 will be slightly larger than the distance A that we had in the previous problem. Okay. Okay. And then besides that, we have the weight of the leg or the weight of the lower extremity acting there. This distance, once again, is B. Okay. And then just to keep things even, let's say that we're lifting the exact same load. So we have the weight of the torso plus WL. Okay. And this distance will be C. Okay. So, just to kind of compare apples to apples here, we're going to try to keep as much of this the same as before. Okay. One thing that does change here is that usually when you lift with your legs, you kind of bring the load kind of naturally closer to your body, and so this distance C and the distance B are probably going to be lower in here as well. But we'll keep them the same. Just kind of for the sake of argument here. Okay. So most parameters are kept at the same value. Okay. So I'm not going to write all those down again. The only difference is that A2, okay. So A2 being the moment arm for the muscle force, okay. So this is going to get slightly bigger. So this is now going to be 0.03 H. Okay. So in the previous problem it was 0.02. Okay. And I'm sorry. Also the attachment angle is going to change as well. Okay. So theta M now is going to be 20 degrees. Okay. So your muscle force is now directed more upwards compared to it was before. Okay. Okay. So, because we kept most of the parameters here the same, our solutions here are going to be the same as well. So, I'm not going to go through and write out the force summation or the moment summation. Okay. So equilibrium equations are mostly the same. Okay. So I'm just going to skip to the result because, how we got this result is kind of the same as before. Okay. So we'll start with the muscle force, and we obtain the muscle force by summing the moments around the lumbar spine. Okay. And so this result here is we get W torso plus WL multiplied by C minus weight of the lower extremity multiplied by B, all divided by A2. Okay. And so just because, just because our spinal erector muscles are kind of in a better position, that A2 is able to grow a little bit, that reduces the amount of force, or that reduces the amount of work that the muscle force has to do, okay? So we plug this in, and we get FM is equal to 3.87 W. So it's still quite big, right? And so, if you're lifting something off the ground, there's kind of no way around it. Your body is going to exert a lot of force, but it's much lower than it was before. I would say maybe it's about 40% lower than it was in the previous example. Okay. Okay. So that's good. So that's a great sign right away that we're in a much better position here. Okay. Okay, so let's compute the joint reactions. And so just like in the previous example, Jx here is going to be minus Fm sine theta m. Okay. So we plug in the value for Fm, we plug in the value of theta. We get Jx is equal to minus 1.32 W. Okay. Once again, it's negative, so all that means is just that we just reverse it. Okay. And then Jy here, Jy is going to be minus Fm cosine theta m plus W of the lower extremity minus W torso minus W load. Okay. We plug in the numbers for this, we get minus 4.54 W. Okay. Okay. As we compute the magnitude, we have square root of Jx squared plus Jy squared. Okay. So this is 4.73 W. Okay. Which again, is much lower than our previous one with poor technique. Okay. All right. Not only is the joint reaction force lower, it's being evenly distributed across the vertebrate bones because your back is up straight. Okay. All right. Any questions on this? Yeah.
Aren't the forces also like in reality slightly lesser because we have some help from the legs are supporting?
That's true. Yeah. So there, you do get some help from the legs, and so in this case, we're kind of still assuming all the forces being taken up by the back, just to kind of do an apples to apples comparison between the two. But you're right, the legs are going to help a bit as well. Yeah. Mm-hmm. All right, so that's all we got time for today. So I have a couple more examples that we'll do on Monday that have to do with kind of workplace, setup and workplace ergonomics. And then we'll talk about just some common injuries in the spine, and then we'll kind of wrap up this section on statics. So thank you guys for coming today. Hope you guys have a good rest of your weekend. Good luck, best of luck studying, and I will see you guys next week. Our question in the chat: what should we do over the weekend to prep for the exam? So definitely check out the study guide. And so definitely check out the study guide that's posted in week 6 on the Canvas site. And then just practice the homework problems. So the homework solutions for problem sets 1 and 2 are on Canvas right now. And then once homework 3 is due, I'll post up for that one as well. Yeah. So use the study guide for the conceptual questions and then practice the homeworks for the problem solved questions. Yep.
So, remember how you said the reaction forces going for the foot?
Yeah.
You set it up like regularly at the locations. So they're negative, would you still get the dash?
Yeah, so, well, the reason we did it for the foot is because we didn't draw the whole body. And so if you were to kind of draw the whole body, let me use a stick figure as kind of a example up here, right? So if you were to do this analysis and find this whole body right here, then you wouldn't have to draw any normal reaction forces for the foot. You would just apply the load directly from right here. So that would apply kind of a downward force here.
Did that change, like your values, because it's in a negative now?
It is, but then, but your body's also kind of much longer now too. And also you're not considering some of the internal forces here as well. So part of the reason we kind of cut it here is so that, the muscle force kind of acts directly at this joint.
Oh, so we just focus on that.
Exactly, yeah. So if you're doing it right here, then your reaction forces, we can't really isolate the joint itself because it's technically an internal force now.
Okay.
And so, you'd be able to compute the normal reaction forces.
I see, okay.
So actually, this analysis right here is kind of, it's almost like we did kind of a static analysis of the whole body itself. We obtained that there's reaction forces here, and then we kind of went internal.
Okay,
right
so
there.
that lets us like focus.
Exactly,
Okay.
exactly.
All right, thank you.
Yep.